Okay, so as I said, this is CMPUT267, and the class is called Machine Learning 1. This should basically be what we expect as your first kind of introduction to this topic of machine learning. And I'm going to be the instructor, and my name is Vlad, and I'll share some more details in a second about that. Okay. So the class and tutorials will all be streamed on Google Meet. There's a link on eClass and the course website, which we'll get to in a second. And all the classes will be recorded, which means the tutorials and the lectures are recorded. The recordings are posted publicly on YouTube. And that means in class, if you speak, your voice might be on the recording. And on Google Meet, if you speak, your voice and your profile picture or video might be recorded. Okay, so this lecture is going to start with a lot of administrative, logistic stuff at the beginning. And then the remaining of the lecture is going to be hopefully me trying to tell you why machine learning is interesting and whether you should take the course. Okay, so there's a course website, and that's the link. So you guys can look it up now if you want. Otherwise, there's a link on eClass as well. And on the course website, you can find the slides, and all future slides and notes and everything like that are going to be on the course website. So if you want to follow along, there are the slides, and you can click all the links and stuff like that. And I'll give you guys like a few more seconds if you want to type in that URL. And maybe what else I should mention is that like most of this, like the course website is basically a copy and paste of eClass with some more details in the schedule and stuff like that, because it's much easier to use a website than it is to use the eClass interface. Okay, so this course is all going to be based on these course notes. So they're in-progress course notes, and these will be updated throughout the term. This is partially because I had the ambitious goal of slightly changing the way the course is structured to make it hopefully easier to understand and follow. So stay tuned to see how this all goes. Okay. And so here's I guess the main info about the course. So the lectures are on Tuesday and Thursday. It seems you guys have figured that out for the Tuesday part at least. And they're in this room, and as I said, they're going to be virtual on Google Meet. Similarly, I decided to have a tutorial for this class, and it's completely optional. And in the tutorial, which is just a little bit later than the class on Thursday, is just going to be a 1-hour session of me or maybe one of the TAs going over some examples and assignment questions and stuff like this. So it's up to you if you want to show up. They'll be recorded as well, so you can watch them later if you want. Okay. And then, so I'm Vlad, and I'm the instructor for this course. And unlike many of your other courses, I'm not actually a professor. So I'm a PhD student. And I'm pretty excited to get to do this. So I've TA'd this course once before, and I think I saw a lot of things that could be changed, improved, or like where students struggle. And I was an undergrad like just a couple years ago. So I think hopefully that perspective will cause for me to be able to teach this stuff in a way that's maybe more interpretable. Okay. And then the office hours, I have office hours right after class on Thursday. And if that's not enough help, we have 11 TAs in the course, so there's a lot of people to ask for help. Again, all this stuff's on the website, so all the slides are just like the bare minimum you should know to start the course. And yeah, there's like at least one office hour every day of the week if you want. And there's like multiple options of in-person and virtual office hours for you to choose from. Okay. Oh, and for contacting the TAs, there's one email for all the TAs, so use that email. Okay, and this is how asking questions and getting help is going to work in the course. So here's my recommendation. I actually recommend your first point of approach is, okay, you can do Google search of things, of course, but like try using LLMs or like AI tools. I think you'll be impressed how fast the responses are of these things and like how quick the feedback and stuff can be before asking any of your questions anywhere else. For two reasons: that like it's only going to get better, and second, I'd recommend you familiarize with these tools. And I have to mention this, which is like LLM outputs shouldn't be trusted. So if you use the output, you should know that it might not be accurate and stuff like this. Okay. So second point of approach for asking questions is Piazza. So Piazza is basically this like forum where you can post a question as a student, and you can post anonymously if you don't want to be seen by other students to ask silly questions and stuff like this. And then the TAs or me will respond. And we have like a TA on duty for Piazza every single day. So you should get a response by that evening or like the next morning or something. So it should be pretty quick as well. Okay, and that's most of your questions should be on Piazza if the LLM isn't answered. Then the next point of approach is going to be emailing TAs. So as I said, TAs have like a course, a joint email. So email them for like private things, like maybe my assignment code doesn't run and I would give away a solution by posting it publicly. So these kind of little things. And then finally, email me if there's like urgent things, like you're missing exams or you have some like private personal issues and stuff like this. But if you can, yeah, go through the first three things beforehand. And okay. And so yeah, join Piazza. So like you actually have to click the link and like just put your name in or something, and then you're there and you can post questions. And once again, links are of all the stuff's on eClass on the course website. Okay, and maybe the most interesting thing about this logistics stuff is how the course grading is going to work, which I guess is the part that everyone actually cares about. So there's going to be a final exam. It's worth the least percentage that I was allowed to make the final exam, which is 30%. Then there's going to be 2 midterms, which are both 20%, and you can see the dates of when the midterms are. And there's going to be 8 assignments, and at least 3 of those are going to be coding assignments using Google Colab. And for some of you, you might have known that this class used to use Julia as the programming language. So this year we're actually changing everything to Python because Python's way more common and almost everyone uses Python for machine learning. So you guys don't have to struggle with learning Julia. Okay, and the last point here, which is like really the only thing you need to do to take this course, or like to have the access to, which is you need an internet connection and you need a modern web browser to use Google Colab. So if you have those 2 things, you can take the course. And obviously, if you want to watch the recordings and stuff, you should have internet. Okay. And here are the wonderful course policies that I have to mention, of course. So we're not accepting late assignments. Just submit the assignment by the date. If it's late, you get 0. That's going to be the policy. Okay. If you're granted an excused absence, which is like for some medical reason or something came up and you have to like ask the department for this excused absence for a midterm, then your weight for that midterm is going to be moved to the final. Okay. And then all the assignments, you should write in your own words. So these are like take-home assignments. So you get to do what you want, but like the policy is you should write them in your own words, and you can use AI or LLMs to help you with the assignments. So this means you can ask them like, and here I should quote, help you, which means like you can ask them to help understand some concepts and stuff. What you shouldn't do is like just throw it into the LLM and ask it for the complete answer and then just copy and paste that in. Okay, so there's no like perfect way or really any good way for us to catch this. But what we ask for you to do at the end of the assignments is just put a note saying like where you use the LLM and how you used it, and just like briefly explain this. Once again, all this is like on eClass and in the course syllabus. And then finally, as you probably all know, there's no cheating, plagiarism, harassment, physical assault, all these other things. And all these can result in very bad things for you, such as this suspension and expulsion from the university. And every year, at least since I've TA'd, I always see at least a few students that end up in this unfortunate situation, and it's not very fun. So yeah, the course should, yeah, I don't think you need to do any of this stuff, hopefully. Okay, and so finally, the actual like proper policy for all this is on this student academic integrity policy, which is linked on the slides and once again in the syllabus and stuff. Okay, and so there's a lot of like minor details of things that I didn't mention, and for that you should refer to the syllabus and the core, like for the proper formal course policies and stuff like that. Okay. And I decided to put one slide in, which is my advice for the course. And maybe this is not so insightful, but I think it's true, which is that, honestly, if you can do the assignments and the questions, like I'm not going to be making the midterms and the finals like to trick you or anything like this. Like it's going to be basically some variation of what you've learned in the assignments and the examples in the course notes. Like I know what it feels like to be a student. I don't know what the point of testing you on things you didn't learn is if the point is to teach you something. So it's going to be exactly what you learned. So just like, if you know the notes, and the notes are like 100 pages, and you do the assignments, which is going to, and then we're going to go over the solutions to the assignments, and we're going to release the solutions as well. If you do all that, I really think you will do quite well in the course. Okay. And here's the disclaimer that this is the feedback we hear every year from this course, or at least I've noticed, which is, first of all, the course has a lot of math. It's supposed to introduce the like mathematical foundations of understanding machine learning stuff, and we also do really the foundations so we don't end up covering neural networks. These are probably the two like biggest things that people should know. However, I do hope that the course notes are mostly self-contained, which means like you don't need to go look at other textbooks and things like this to understand all these details about math and stuff. We really try to put it all in the course notes. So if you read the course notes, you should know all the math you need. And finally, I'm going to try my best to really motivate why we're doing any of this math, because as I've seen before, people or like students can really learn all the math and maybe get into it, but have no idea what the point of anything is. So that's going to be like the main motivation, like behind a lot of this. Like I'm really going to try to make this intuitive for everyone. Okay, and finally, here's some like necessary like prereqs and stuff. But in words, it's basically if you can take some derivatives, that's really the only thing you need to know that isn't going to be covered in like the necessary details. Even though we're going to really give you the rules of like, here's how you take the derivatives of common functions, and that's all we're going to use. So maybe even that's not that necessary. But if you've taken like probability and statistics courses, or you have some familiarity with linear algebra, like the term called a vector or a matrix, then you're, I guess, better off for this course than otherwise. Okay. And yeah, so this is like, I really encourage people to ask questions, and in particular, like asking the question of why we're doing anything. Because this is a classic problem that students run into. They do all this math in this course, and they have no idea why they're doing anything. So like, please ask this question of like, why am I ever introducing any math concept if it's not somehow useful to the future or something like this? So this is what I encourage the most to be asked. Okay. And here's the course outline, which probably won't make much sense right now, but the goal is with the rest of the slides, we're going to come back to it at the very end, and you're hopefully going to understand everything in this course outline and what this looks like in some broad sense. Okay. So we're going to start with math and probability review. This is like what I mean by it's self-contained. It's just going to give you all the little like math and probability tools you need, like specifically necessary for all the machine learning parts to come. Okay, then we're going to define what the problem we're trying to solve is, which is going to be called this supervised learning problem. It's like a subset of possible machine learning problems. And it turns out it can be split into these two type of common versions of supervised learning called regression and classification. And so what we're going to do is we're going to just design some learning programs or whatever. We're going to design ways to solve these regression problems. And then we're going to have the first midterm. So before the first midterm, what you should see is like, here's the problem, and here's some simple ways to solve it. That's what you're going to be tested on. Then after that, we're going to like evaluate what our solutions were and see if they were actually good ways to solve the problem. And then we're going to see like, oh, maybe there's some issues with these solutions, and then we're going to update them a little bit and have new solutions, and then compare those to the previous ones, and that's going to be midterm 2. And this is all going to be for regression. Okay. And then after midterm 2, which is like midterm 2 is right after reading week, there's going to be maybe like 4 or 5 more lectures, and we're going to go over this other set of problems called classification problems. And these, as you'll see, you're probably more familiar with in machine learning world. And we're going to repeat basically everything we did before, but now we have like all these tools and things, so it's going to be very similar, and it's going to be a lot quicker. And then if we have time, maybe we'll see how much time we have. We can go over some like brief introduction into these language models, and you'll like ChatGPT and stuff, and you'll see that like basically all the tools you learned are there, and you could already like see how you could implement something like this, because it's really not that different. So that's going to be quite interesting. Let me just mention one thing, and I'll take your question. And then yeah, so the final exam will then basically be cumulative, and the only new things will be this like logistic regression thing. And so at this point, this is all the logistic stuff. And is there any questions? And I guess you had a question. Yeah, so just to repeat for, I guess, the recording stuff, the question was, are the midterms kind of cumulative or not? So obviously the first midterm, there's no notion of being cumulative. The second one, we're going to focus on this like evaluating of the algorithms or the programs and like the new programs and stuff, but it will definitely be necessary to understand the previous stuff, which is like, what is the problem you're trying to solve? And then since the algorithms and like they're going to build on the previous ones, it would be very hard to not know the previous one but know the new one. So in this sense, like it's cumulative, but like inherently cumulative, not like, yeah. Okay. Is there any other questions before we get into the rest of the presentation, which is all the motivational stuff and no more of this logistics and stuff like that? Okay. Okay, I guess everyone's happy with the course. Good. Let me just see if there's anything online. Yeah, so also like if you join the course on Google Meet, you can ask questions and I will see them on my iPad and I will answer the questions if I see them, hopefully. Yeah, another question? Yes, that's an important thing. So the midterms are going to be in class. They're basically the only two things that you need to be in class for. They're the full class time, so it's like an hour and 20 minutes, both the midterms, in this exact same room. Yes, that is very important. Thank you for asking that. So once again, those are the only two times you should make sure that you can definitely come to the class. Okay, cool. So let's begin. So I really hope to communicate what is this machine learning stuff and why should you be interested in doing it in this class. Okay, so let's start. So I just wanted to get oh yeah, and I wanted to mention like these remaining slides are somewhat based on this other professor called Shai Ben David, and he teaches this course, which is like a more theoretical version of machine learning than this will be. And it's a fourth-year course at the University of Waterloo, and I think they're some of the best lectures like ever. They are quite math-heavy, but I think he does like a really beautiful job. So if you want something like more advanced in this course, look at that one, and also like, yeah, I used some of the stuff from his lecture to talk about it. So to start, I just wanted to get an idea of like everyone's knowledge of these topics and interests and stuff like that. So I'm not gonna like pick any of you for any of this. It's just like, can you just raise your hand if you think you know what this machine learning topic even is? Okay, so for people online, this is maybe like 30% of the class. That's actually lower than I expected, so that's good to know. Okay, and then maybe raise your hand if you've ever taken some sort of machine learning course on your own or like watched videos and stuff. Okay, it seems very similar to the previous one, so like maybe 30 or 40% of the class. Cool. Okay, so now raise your hand if you've heard of what ChatGPT is. Okay, good. So most of the class knows what ChatGPT is. Very nice. And how many of you actually use it, like on your day-to-day basis for doing like your work and everything? Okay, so probably more people than the number of people that said they know machine learning. So maybe like 60%. Interesting. So ChatGPT is an example of like an algorithm that is a machine learning algorithm. Okay. And finally, like raise your hand if you're actually excited for machine learning or if you just like took it randomly because you need to or something. Okay, so probably more people than the number of people that know what it is. So also like 60%. Cool, maybe the same people that use ChatGPT. And so yeah, I will like, I hope that at the end of this you will sort of understand how ChatGPT, like why it works fundamentally, okay. Okay, so now we start on this question that I wanted to answer, which is what is this machine learning stuff? And the answer I'm going to give next is not going to be so satisfactory probably, which is that I'm just like, for this course, it's going to be just a program or algorithm that is learning. Okay. And then the real question becomes like, what is this learning business that I'm talking about? And we're going to spend quite a bit of time talking about what this learning stuff is. Okay. So I'm going to define this learning stuff as this. So let's take this. So what it's going to look like is that there's some sort of experience, then you do something called learning, and then you acquire knowledge. Okay, and to sort of convince you of this, I'm going to give a lot of different examples, and I'm going to point out how there's all sorts of different kinds of learning and stuff, and which one we're going to talk about. Okay, so like maybe, yeah, I would do a disservice not to mention this classic example of learning stuff, which is this psychology's famous experiment called Pavlov's dog. So in this experiment, there's this guy named Pavlov, and he was doing some studies, which I'm not going to go over all the details, but the point is, he rang a bell, and there was a dog. And then after he rang the bell, he gave the dog food. Okay? And so, long and behold, after he did this many times, the dog learned that the bell implies food. Okay? So, lots of experience, and then what's the knowledge? The knowledge is food, or sorry, bell means food. And then there was, like, obviously, there's these other parts of the experiment which, like, the dog ends up salivating when the bell rings, but that's because it's expecting, like, it's already predicted there's going to be food, and salivation comes before food, just for the details. Okay, so that's one example of learning. So here's another example. So this is actually like I guess a personal one. So I started playing tennis like not too long ago, like a few months ago. And so here was the story, and I think this nicely highlighted different kinds of like learning that we're going to see. So I started playing tennis, but I didn't really know any of the rules. I never really like properly watched tennis or anything. I just had this tennis racket. Oh, okay. Yeah. Is it someone on someone's computer? Oh, wait a minute. Okay. So yeah, I didn't really know how to play tennis that much. Like, I mean, I didn't know the rules or anything. I just had this racket and I had a ball. And I was like, okay, so I'll just hit the ball around and see what happens. So I just like played by myself basically against this wall for a little bit to figure out, like, I had this racket and some tennis balls. And so what did I acquire? I acquired this like knowledge of, I guess, some hand-eye coordination and like ball control and stuff, but I didn't really acquire the ability to learn tennis. I just kind of understood how the ball and the racket and stuff works. So then after that, I was like, okay, I should probably learn how to play tennis. So what I did is okay. So this is called what we're going to call unsupervised learning. So there's like no supervision. It's just like you have the stream of data or knowledge or stream of experience, and there's no notion of like what is correct or wrong. You just like kind of understand the data. So then I sat down, and then I decided to watch a YouTube video to understand what is this game of tennis and stuff and how to properly play. And so what this looked like is like someone being like, hey, when you're in this position on the court, you should like swing with your hand, like a forehand kind of swing. And when you're like on this side, you should swing with like a backhand thing. And then when you're serving, you can serve like over your head and stuff like this. So the point is there was many different like places on the court, and I was told exactly what I needed to do. And so what this gave me is like, I argue some knowledge of how to play tennis. Okay. And this type of learning, we're going to call a supervised learning. So here you have like clear labels of what you should do in certain places in the world. So this is the kind of, so it's a different kind of experience. So, okay. And then then after this, what I did is I didn't just keep watching these videos. I actually started playing. So I started playing tennis. And what this looked like is I'd be in these different positions, and I didn't know exactly what I should do, because like it's not exactly like in the video. You know, I'd be slightly in a different spot. So I'd do something, and I wouldn't get like the perfect feedback. I'd get something saying like, oh, I kind of like didn't get the ball over, so I probably did something sort of wrong. And so this kind of feedback is not like this perfectly labeled data. And it's going to be, okay, so similar thing. The knowledge I got is how to play tennis. And so this thing is called reinforcement learning. Okay, so these are like commonly introduced 3 branches of machine learning and kind of like the biggest 3 classes. There's this unsupervised, so there's no labels for your data. There's supervised, which is like you have like some, we're going to call like some context or something, or yeah, some context of the world, and in that context, it tells you, here's what you should do. And then finally, there's reinforcement learning, which is you get some form of feedback, but it's not like it tells you exactly how you should act in that situation. Okay. So that's an example. So that was like one certain types of learning. So now we're going to go on to learning language. Okay. And so here, the first case of learning language is going to be how language models actually learn. So this picture is supposed to show, this is supposed to be like all of the language and text on the internet. So it's this giant thing of all these books and, I don't know, all these emails and files. It's giant. And so this is your data. And then what happens is people train on this giant set of experience and data, and you produce ChatGPT and other language models. Okay, so ChatGPT would be called the knowledge part here. So so there's something that's done some learning with all this data, and it produces knowledge, which is now ChatGPT, which is like you just give it some prompt, and then it gives you the correct whatever answer to that thing. Okay. This is quite okay. So this and notice how there's like it looked at all of this data beforehand, which is like the whole internet, and then it produced what is, let's say, something that can speak English or like speak a language. This is in quite the stark contrast to maybe how humans and kids and stuff learn language, which is you might like, you know, get a lesson in school for like an hour or whatever. And then after that, what you do is you like have to actually maybe present it or interact with other people and stuff, and you get feedback pretty soon after you've actually gathered a little bit of data. And then after that, you go and gather more data and so on and so on, and this thing kind of repeats. And this kind of learning is actually called like online learning. And don't worry about keeping all these like names in your mind. It's going to come back in a few slides. So I just want to get you guys like familiar with these kind of, there's all these different types of learning. Yeah, and so what you don't do is you don't like sit down, look at all of the like text and everything, and then like and then can go out and like live your life and stuff. It's really this like iterative thing. And so here's the final example before I kind of explain what kind of learning we're going to talk about in this course. So here's an example of games. So here's 3 slot machines. And what you should think about is these slot machines have some like random chance of you winning or not winning. And let's say they're all different. So maybe like the first one, let's say you only win or you don't win in these slot machines. You like either get $1 or you don't get $1. So you should think of the first slot machine as, let's say, like has like a 20% chance of winning. The one in the middle maybe has like, the first one has like, let's say like a 40% chance of winning. The one in the middle is like 30, and then the one on the right is like 20. So if you play and keep playing these slot machines, you might notice, okay, I'm winning more often on this red machine. So what does that mean? It means I should probably play the red machine more often. But notice how like your data here is arriving in this like random fashion. Like you're just playing these slot machines and they're just randomly giving you some sort of data. And so this kind of learning is going to be called like stochastic learning, and really what this stochastic word communicates is that data is arriving to you in a random fashion. Okay? So there's no one's handpicking the data or anything. It's just like you play the thing, it's randomly samples from whatever something, and then you get this whether you win or not, and so on. Okay. So this is different from like many other games, let's say, where you actually play against an opponent. And so here the opponent is trying to make you lose. So there's like the data is not like you're just playing this game and you randomly the person does some move. It's like they have some intention to make you kind of suffer and do as bad as possible. So this in here you'd have a bunch of you play a bunch of chess games, and then then your knowledge is that you can play chess afterwards. But importantly, the data is called this like adversarial data, and this would be called like adversarial learning. Okay, so this is like a different type of learning as well. Cool. So the question is, I've like mentioned all these different kinds of learning already, and at this point you might be wondering like, okay, like what are we going to do? And maybe to even mention, there's all sorts of other ways people have also tried to like break up. Like there's these, but these are probably the biggest like 3 main ones you'll hear and stuff like this. And so we're going to be covering this class a very specific setting, which is it's going to be this supervised learning. So that means you're going to have like labels. It's going to be this offline batch learning thing, which means you have like this giant set of data that comes to you from who knows where, but you have it all at once. And then it's going to be stochastic learning, which means it's just like random samples of it. So maybe like you gathered random samples of people's height, or you did some survey or something like this. Okay, and so it turns out that this setting, although I said like they're supervised, offline, stochastic learning, and whatever, it turns out all this is really just usually grouped into the word of supervised learning. So when someone says like they're doing supervised learning, it usually just means this. So whenever you hear that, it means that like someone really had this batch of data and so on. And like if you kind of forgot what these things mean, even though I've mentioned them, I guess, a couple times, here's like the informal way to like remember these, whatever. So what we're going to learn about in this course is learning, whatever learning, we'll get into those details in a second, but like we're going to, supervised learning is going to be this thing where you're learning from a batch of labeled and randomly selected data. Okay. Or randomly selected experience data. I guess you'll notice that I'm going to use the word experience and data interchangeably throughout. Okay. Oh, and just to give like an actual example that Hannah has all 3 of these is this example of spam detection. So this would be like spam detection for emails or something like this. So here you have this giant batch of like you might imagine how you would train something like this, or like a computer would learn to do something like this. So you had this giant set of examples of all these emails. Some of them are labeled spam or not spam, kind of like in this picture here. And these emails are just randomly selected. They might like be just from random people's inboxes that are okay with sharing this stuff and whatever. And yeah, so this is this giant batch of data. It has labels, which is this is spam or not spam, and it just randomly selected. And then what you would learn is how to produce a spam detector, which means if you see a new email, should I say whether it's spam or should I call it not spam? Okay, so this is the kind of examples we're gonna see in this course. Okay. So before I get to this question, is there any questions about just like, yeah, go ahead. Is unsupervised learning before supervised learning? So the question is unsupervised learning necessary for supervised learning? The answer is no, but you also mentioned as per the example. So which example do you mean? Oh, yeah. So that's not necessary. You could have, if you just go back here, you could have just immediately jumped to watch. Like people will usually just have get tennis lessons before needing to actually you don't need to waste this time playing around on your own without knowing the rules before getting supervision. Yeah, so it's not necessary. Go ahead. Yeah, so, okay, maybe one thing to mention is, so for this, okay, so the question is, what's kind of the difference of supervised learning and reinforcement learning? And so I just want to point out for this lecture, I'm really trying to cover things at like a high level. So I did say this course is going to be like math heavy and stuff. There's going to be almost no math. Well, there's going to be basically no math in this presentation. It's just to get you kind of like a high level understanding of these details. So don't be surprised if some of this seems a little bit foggy and imprecise. Okay, so we will go formally over what supervised learning is later. But just to highlight exactly what I meant here one more time. So here you're trying to play tennis, right? And so your experience here for the supervised learning thing would be something like, if you're in this position on the court, here is the correct way to like, let's say, to act, which would be like swing my racket or whatever. And what that kind of implicitly implies is like, here's everything else is not correct. Like this is the correct way you should act, and then therefore I know that everything else is like not a good way to act or something like this. For reinforcement learning, if you're in this position and you swing your racket, you don't really, like something happens and you get some feedback and you're told only about this single action, that this is like, maybe wasn't the right one because you lost the point or you missed. Or if you got it and you're like, okay, this was good, but like maybe it wasn't perfect, but like you don't get all this information. So the point is, you're missing the information of like what is the correct action, and like, yeah, you're basically missing all the information about all the other actions. While in the supervised learning thing, you get that, like by getting the correct action, like you're told the correct action, you immediately know that all the other ones are like wrong for you. So this is how we're gonna like, this is the kind of high level way to think about it for this. Does that answer the question? Okay, yeah, up there. Yeah.
That would be supervised learning. Right?
Yeah.
But is that the algorithm, not like the algorithms that you're developing to label what email is spam and not spam? So like if the email is already labeled what like as spam or not spam, doesn't that defeat the purpose of the algorithm?
Right. So I think the next slides will actually make this a lot more precise, but just the point of the question was like, if the spam like data, which is you have an email and you label it spam or not spam, doesn't that defeat the purpose of the actual algorithm if the algorithm should be the thing labeling it? And so this is like goes to a key point, which is that in the experience, you actually kind of have the behavior you want your algorithm to perform. So here it'd be like, you have an email and you have its correct label. And so this is the knowledge you're trying to acquire, which means that if I get a new email without a label, can I label it correctly? So that's what the spam detection would be. It's like, I have a bunch of examples of how I should act, which is like emails and then the correct labels. And what I need to produce is this knowledge, which is a spam detector, which takes as input only a new email, no label, and I can then produce the label. Okay. Cool. So let's move on to trying to tell you why. So you saw some examples of like humans learning, you saw some examples of maybe machines learning and stuff, but like at the end of the day, why do you really need these machines that learn if you could just have humans that learn? And so maybe you're asking this question, maybe you're not, but we're going to address it. So I'm going to give some examples of first why programs or like machines are useful to begin with. Nothing to do with learning yet. Okay. So and the claim I'm going to make, and there's probably lots of other like nuanced things, but like the main reason is that these programs, and I'm going to use programs and machines interchangeably, is that these programs can perform computations much more efficiently than humans. So like an example is a calculator. So you can do math, like a human can do the steps to solve math problems, but like it's just so much faster to have some program that computes this answer for you much quicker. Another example is maybe Excel. So you can like plot things, like of course a human can go and plot every single data point of like maybe everyone's height in like a country, but that would be very annoying. Here you just put it into Excel, it just generates the plot immediately. Okay. So once again, I just want to highlight these are not learning algorithms yet. These are just normal programs that you've heard of. And once again, I'm also going to use the word algorithm, program, and machine kind of interchangeably as you'll hear. Okay. So Google Maps. Once again, you could probably plan your route to get somewhere, but you just put it into Google Maps, I'm here, I want to go there, and it somehow does the search of like, okay, this route is faster than this route and this route, so then I pick that or something. Okay, maybe like Google Docs, you can count the number of words. Imagine trying to like submit some document and you had to like manually count all these words. But once again, these are all examples of like things you could do, but the program, what do? You like tell the program the steps you would do, and it just does it way faster. And so on, there's like other examples of all sorts of programs and software and things like this. Okay, cool. And so I'm going to call these kind of programs that I just mentioned these kind of classic programs. And this is what usually you're like used to with programming here. And it looks like this, which is that a human writes some code, and from that code you get some knowledge, which now we're going to talk about knowledge as programs. So so it produced some knowledge. So here, like it would be, example, human writes a calculator program. So that means you write some code, the calculator has like some code, and then what that means is then it can add numbers. And this would be like a human literally saying in the program something like, if the number is this, then like carry it over if it has like a number in the tens place or the hundreds, and like you give these manual instructions. So you can think of a program as really like a set of instructions that a human has outlined for what it needs to do in order to succeed. And usually the human actually needs to know how to solve this problem, right? To then program it, to then have the machine do it, but do it more efficiently. Okay, there was a question online, and the question is, will we be programming with different libraries to create these ML models, or is it more open on more pen and paper problems? Oh, yeah, yeah, I guess you guys heard the question is like, are you going to be using machine like libraries to train machine learning models, and is it going to be more like pen and paper problems, which I don't exactly know what that means, but the assignments are going to look like this, which is there's 8 of the assignments. The first 4-ish or so are going to be doing more like math and doing pen and paper and just like writing things out of like, here's the math and here's defining the problem and the algorithm. And then the later assignments are mainly going to be the programming ones, in which you're actually going to implement the things that you like did the math to understand and learn and stuff like this. And most of the implementation, so you're actually going to implement the algorithms or the programs, but you're going to implement it like kind of from scratch, which means you're actually going to do all of the like different steps for learning on your own. You're going to implement all those steps. And this is as opposed to using libraries to do this for you. So there exist libraries where you can literally just pass in like experience and it outputs to you knowledge, which is like the program that can, let's say, do spam detection. But what you're going to do is you're actually going to implement that whole thing. And the slides will come that I point that out. So there's not going to be many libraries. The assignments aren't like fully decided on and made and stuff. So we'll see how things are going. Maybe the last one or something, you can implement some like bigger model using tricks and stuff that aren't exactly covered in the course, but is more fun, and you can like see it work and using these libraries to train and things. So yeah. So yeah, if you guys ask these questions on Piazza and stuff, maybe if there's enough interest, we can make the last one like more exciting of an assignment or something. Cool. Okay, so these are the classic programs. So I just want to point out like, what would a learning program kind of look like? And so that I already indicated this is what the learning kind of experience looks like, or like a learning process. You have some experience, then you have learning. And I'm going to claim that the learning part is also a program. And this is, well, I'm not going to claim this is what it's actually going to look like, is there's learning, that's a program itself, and it's going to produce another program, which is the knowledge part. And so for the calculator example, that might look something like this. So you have the calculator that actually looks at examples of math being done. So like maybe let's say numbers being added together and stuff like this. So to actually look at this, somehow decide on how this is done, like what are the steps to do this. No one's actually telling it, like if there's 2 numbers, say you add it. All it sees is just a bunch of examples of like one number plus another number and the output, which is the correct answer and so on. And then you would produce a calculator. So this is what like a learning algorithm might look like for the calculator. But you might still wonder at this point, like why in the world do we need this learning algorithm if I could just write the program for the calculator? Do I really need this calculator that can look at examples like a human would and then understand how to add numbers? And so now I'm going to argue finally why these programs that learn could be useful through some examples again. So once again, it's really asking, why don't we just write the code for certain types of, the reason why they're useful is that we sometimes don't actually know how to write the code for certain types of knowledge, which I mean like we actually don't know the step-by-step instructions on how we do certain things. So one example might be like creating an image of something, like you ask a painter of like to write or define all the steps that he took to make a painting of like some beautiful, I don't know, a cat or something. It's going to be hard for them to explain it, but they can do it. And they can produce examples of like what a beautiful cat kind of looks like. And so, yeah, so one example is like, let's generate an image of a cat. So imagine trying to explain the steps of how to write imagine writing a program which is like a program that can generate images. That would be quite hard. Or maybe an even harder task would be like, let's generate an image of a person that can't explain the steps to draw the cat. Okay, and so so it turns out that we actually have programs that can already do this. So I already put this into Chat. So I put this into ChatGPT and it generated this picture for me. And actually, just so you guys know, every single picture so far in this presentation was generated by ChatGPT. Okay, so you can imagine if you wanted to generate all these pictures and like write a program that actually did this and like manually say like, if someone wants this, then like draw like that, and if you want this, then it'd be really, really challenging. So here, like ChatGPT was trained from just seeing lots of examples, and so here ChatGPT now is like this interface where you can generate images and output text and so on. Okay, so it's not just doing language. And so the way it was trained, well, as you saw, is it has this giant thing of not just text now, but actually like text along with picture. So now it knows what text refers to what picture. Okay, and let me cover some more examples. Okay, so imagine trying to like do object detection. This is a classic thing for like self-driving cars. So an example here, also generated by ChatGPT, which is like you have a stop sign, you have these lights, you have a person. Imagine trying to like write a program to detect these things. You'd be like, okay, if the person, like if there's maybe a change from white to dark, but what if the person's then change the shirt, then how do I detect the person's shirt relative to, so you can imagine like writing these rules would be really, really challenging in a usual programming way. Okay, so all these like self-driving stuff are all doing this image detection things using machine learning algorithms. Okay, more examples, these chatbots like ChatGPT, there's other ones like Claude and Gemini that are pretty popular. You can, all these have like some free usage, so you can use any of these. And maybe another really interesting direction that this stuff's being used for is that like, I was kind of explaining the previous ones, which is like, we can like produce images of cats, or we can like detect these objects in the pictures, but maybe we don't know how to actually define the steps we took to do this thing. Well, it turns out that there's other things that like we can't even do ourselves. So then imagine trying to write a program for something we can't do. Well, it turns out that like these machine learning algorithms can kind of solve these problems. So one kind of famous example here is this protein folding problem. So in biology world or whatever, there's these things called amino acid chains. They're also called like peptides, I guess. And they're basically just like proteins are made of these tiny amino acids, and when they connect, they form a chain of amino acids. And it turns out when they connect, they form these like complicated three-dimensional folding structures. So that would mean like you have this amino acid chain, you have many of them. They then do some weird folding, and they become something like this. So this is what a protein actually looks like. So it's really useful, it turns out, to be able to predict from this chain of amino acid what will the protein look like for all sorts of, I don't know, biology-related research. And we didn't have a program that could do this. And people tried to like manually write programs thinking like, oh, maybe it follows these laws of physics and stuff. But that was always really hard. And then I think like 2 or 3 years ago, DeepMind, which is a company owned by Google, came out with this program called AlphaFold. And all it did is it looked at a bunch of examples of labeled data, which would be like, here is the amino acid chain, which tells you just like, this amino acid is connected to this amino acid and so on. And then the label would have been, this is what the three-dimensional structure looks like of the protein. Okay? So it just looked at all that. And then from that, it was then able to see a new example of an amino acid, something maybe that biologists, whatever, wanted to create a new amino acid, and they want to know what does it look like when it gets folded up in 3 dimensions. And so this kind of program was then able to actually achieve this with pretty decent accuracy. Like I think the best before this was like 60%, and this was achieving like over 80% accuracy. Okay, so a lot of science discovery stuff is like very promising for this kind of applications as well, and it gets very cool. Okay, so that was the first reason. It's just like you can't define the instructions yourself. So you just show it examples, and hopefully you can learn the instructions to get there. And maybe the second reason is that you can adapt to changing environments. So I just have one example here for this, which is like, once again, imagine you want to do object detection here, and you want to detect a picture of a dog. There's all sorts of ways the dog can be oriented. Sure, you can maybe do this and like write the instructions to do this. But then imagine, oh, now you want to detect these dogs in the nighttime, and then in the nighttime, you see that, oh, now the colors are all different, and maybe in my program that I wrote before, I had these very specific instructions that the dog was maybe brighter than the background, or like whatever, this color change. And now I have to go into my program and change all these instructions and rules, and hopefully it works for the night and the day and stuff. But if you had this machine, like this learning program, all you would need to do is give it examples of dogs in the nighttime, and then it should apparently learn that these are dogs in the nighttime. So like, once again, the data would look like picture of dog, and then label, which is like maybe circling where the dog is. And then what you would get as output is a program that sees only the picture and then can circle the part where the dog is. Okay. So yeah, so that's explaining why these programs that can learn are useful. Okay, so hopefully at this point you've kind of briefly seen what learning algorithms or learning programs look like, and have some reason to believe that they're actually going to be useful. So at this point, I want to cover what are you actually going to do in the course. So, and with some like maybe more concrete examples of actual things you're going to implement and stuff. So yeah, so as I said, we're going to cover this setting, which is the supervised learning setting. Okay. And yeah, and this really says something about what is the type of data or experience you're going to be using to learn from. And maybe, okay, I'll cover one more thing and then go. And this is what it's actually like more of what it's going to look like what part you're actually filling into this process. So what you're going to learn is you're going to learn to write a program that learns. And what that looks like is, I said we had this like, once again, this diagram, which you've seen a lot of times now. And what you're going to do is you're going to fill in this block. You're going to fill in this learning part. So that means you're going to write a program. And what that really means is there's still going to be this step, which is that a human writes code or writes a program. But that program is now going to be a learning program. And the person writing the code is now going to be you. So you're going to be writing code, and that code is going to be a learning program. And then what you're going to do is you're going to put it right into this process here, or like the learning part. You're then going to have your learning program take in experience, and then produce another program, which is going to be like labeling things or whatever, something like this. Okay. So the next things I'm going to do is go over two like more concrete examples with actual, let's say, like proper data, and they're kind of simple, and then the things you're actually going to implement. But is there any questions before I do that? So this image, I really hope communicates exactly like what you're going to fill in. So once again, instead of like writing this program from scratch, you're going to write something that learns to create the program for you. Okay, cool. So let's move on. So yeah, so here are like concrete examples of what this might actually, what this will look like. Okay. So here is an example you will see in many machine learning books. And this is the example of predicting house prices based on some information about the houses. Okay. So here I just have one piece of information, which is called the number of rooms. So this would mean I have experience that looks like this. Here I have four data points, I would call it, which is I have some house and I know how many rooms it has. And then I have the price that it was, let's say, sold for, something like this. And then I have another house which has like 4 rooms, and then I know the price that was sold for, and so on. So this is a very specific example. You can imagine that for houses in the real world, you have more information. Maybe like you also have the size and the place in the city they're located, and I don't know, like how many bathrooms it has, and all this kind of information. And so that would be kind of like what we're going to call is like the features or the context, and this would be everything to the left of here. And this thing on the right, this price, is what we call the label. Okay, so yes, so okay, we'll cover that in a second. And so that fits into like, this is what experience looks like for a real like programming task, something like this. So now, okay, so what is our goal? Our goal is to like somehow use this thing to do some learning on it and produce some sort of knowledge. But what does really like knowledge look like? And we're going to talk about different kinds of knowledge later on when we get more formal and stuff later in the course. But for this, hopefully you'll agree that some useful piece of knowledge from this would be to learn something called a prediction function. So this prediction function, or sometimes it's called a predictor or whatever, would be a function that takes as input the number of rooms, which is the information about the house, and then it's going to produce the label, and it's going to produce the correct label, right? So this is, from here you should see that you have examples of number of rooms and the correct labels. And what you want to do is you want to produce a function, this predictor function, that's going to take as input the number of rooms, but it doesn't know the label, right? And then it's going to output a label, which is the correct label. Okay, so and more precisely, what that's going to look like is you want to write a learning program, right? So and then you're going to put that learning program into here, and that is a program. And that learning program needs to output a predictor f. Okay, and that's this predictor function. And this predictor f has to satisfy this property that f can predict the price of any unseen house. And it can predict it well. Like perfectly is ideal, but like, you know, you're going to measure like something close to perfect is also pretty good. It depends what accuracy you want and things like this. But that's your goal. That's usually what things are going to look like, which is like you have some program takes some data, and then it's going to output some sort of like function, and this function is like your knowledge, or like when I say function, you can think of that as a program. It's anything that like takes in data and outputs like the label. Okay. So that's a more concrete example. It's not done yet. We're going to actually like show more details of what this looks like. And I wanted to highlight that this is really an example of a supervised learning problem. So why is that the case? That's the case because what we have is we have a batch of data, right? So here we only have 4, we would call like data points, but we have 4. So we have this batch of this data here. All of it is labeled, which means we actually know the correct price for each of the houses. And finally, we're going to like, this should be sort of this is what we're going to assume, but it's kind of makes sense, I guess, in this setting, which is that we just randomly sampled some houses. We just like maybe got some, randomly chose it from the internet of examples of houses that were sold for this. There was not like some person that adversarially was giving me examples of houses that had weirdly sold for way more than they were supposed to, such that I couldn't learn, right? So so these are going to be the really big foundational assumptions we're going to make in the supervised learning setting, and we're going to once again make them like concrete later in the course. Okay. So let's see what this actually is going to look like when you try to implement it. So what that's going to look like is you're going to have this data, and then you might plot it to see what it looks like. And that's going to look something like this, which is here you have the number of rooms in the house, and then you notice that, okay, so then you plot the house price, and then these are the four data points, and you notice, oh, it seems that as the number of rooms increases, the house price also increases, or something like this. So this is maybe an overly simplified example, but it highlights the point. So maybe here you don't need this computer that can learn from this, but we'll still highlight what this would look like using an actual program that you implement. Okay, so then what happens is then you are going to write this learning program, which is going to look at this data and somehow try to produce a function that can predict, once again, the prices for new houses. So what that looks like is maybe something like this. So you have this learning program, and I'm going to call this a simple learning program. So I've implemented some program here. And it's going to produce this red line. And this red line is going to be called your predictor function, right? So why is this like a predictor function? Well, you can think of the red line as for any point on the x-axis, it's going to output a price on the y-axis, okay? And so, yeah, so you produce something. Here's a more complex learning program that I use to produce a predictor. It's a different predictor now, so there's a different red line. And you can see that this red line more accurately fits the blue points, okay? Whatever more accurately means in this. So take that with a grain of salt for a second. You can see it more accurately, like actually goes through all the blue points in your data. So one might think, okay, maybe this is a good predictor because like it perfectly labels all the points in my data set, right? While this other I wanted this line, you know, is kind of off for this point and this one not per, and something like that. But really, remember, the goal was that if I see new data, I want to predict that well. And so what would that look like? That would mean like, okay, here's some new data, and here's what my line now looks like, that line that I chose looks like. So I just assumed that the new data would actually look something like these green dots. I hope you can like agree that that would sort of make sense, whatever that means. And you can see this line like sort of does okay. And here's what the more complex one looks like, which is the one you learned before. You can see that it's like not so good as you might think. It's okay here, maybe not the worst. But then like for later house prices, it's just terrible. Okay. So here you're going to immediately see that there's some sort of like trade-off between how well do you do on the examples you've seen and relative to how well that means you're going to do on new unseen things. Okay, and there's going to be this really, I'm just going to throw these kind of terms out in the open, and we're going to define them more properly later, but hopefully that makes sense, which is this more complex one is going to exhibit this behavior we call overfitting. Okay, so it means it's overly fit to the data, and what that means is that when it sees new data, it doesn't actually predict it well. Okay. So this is like one common problem that sometimes happens. And interestingly here is I actually use, for the more complex one, I use a neural network. So you can see here already, it's like, it turns out that a neural network might not be, okay, like whatever. It's not always the best if you just implement a vanilla neural network with no other tricks and stuff like this. And it happens like this. And okay. Cool. So that's one example. I'm going to go over like a different kind of example. So there you saw there was like these house prices you're trying to predict. And I'll mention later, but that kind of a problem is called this regression problem. So if you took any like statistics course, you would have heard it as a regression problem. And I'll define it a little more precisely in a couple slides. But now we're going to look at another example, which is called these like classification problems. So here's an example of a classification problem. And this is called classify. Okay, so the example here is classifying wine. You can imagine classifying very many different things, like classifying pictures of, let's say, like numbers or cats, like a classic other example is cats and dogs. You see pictures of cats and dogs, and you want to be able to classify whether this is a cat or a dog. But then you can imagine it's much bigger. It's like you have thousands and thousands of different objects like cats, donkeys, pencils, water bottles, and you want to somehow classify these. Okay, so classification turns out to be a very important problem, but we're going to study like a very simple case here. So this is a case of wine, predicting the wine. So in this case, it's either the wine is this Barolo wine, or it's not Barolo wine. Okay, so there's two classes, either Barolo or not Barolo. And the information you have to make this prediction is these two chemicals that exist in every wine, or most wines, which is proline and flavonoid. Okay, so this actually is like a real example of a real data set online of predicting the type of wine. So once again, you have these two chemicals, and you have the concentrations of each of them. I don't actually remember what is this measure in milligrams or grams or whatever, but some measure. And this tells you how much proline do I have in my wine, how much flavonoid do I have in my wine, and here is the type of wine it is. Okay? And so here you actually have much more data points, and in this case, I used 50 data points, so much more than 4. Okay, so once again, this is what the experience part looks like. And our goal, once again, is to produce a prediction function. Okay, and what does this look like? Here, it's not like the number of rooms that I'm taking as input. Instead, I'm taking these chemicals. And notice here, the function takes in 2 inputs, which is both the chemicals, right? So an example would be like I take in as input 3, like 3 here would mean that's the concentration of proline, and the other 3 means this is the concentration of flavonoid. And what that produces is the label for the wine. Is it Barolo or not? So maybe this predictor here produces, it says it's Barolo if it's this. Okay, and then once again, the objective is something like write this program, which is in the middle, that outputs this predictor, right? That outputs another program that can, what can this other program, this predictor F do? Well, this F can predict the type of unseen wine, okay? Okay, and that's, once again, a supervised learning problem. Why is it a supervised learning problem? It's because you have this batch of data. The data is labeled in the sense that you have these chemicals, and then the label of what type of wine it is. And then it's randomly selected. We're once again assuming you've just somehow gathered this data randomly. It wasn't someone like adversarially trying to like trick you with giving you these wine labels and stuff like that. Okay. So what does this look like in terms of you implementing it and plotting it and stuff? And this is, you're probably gonna do something like this in one of the assignments too, which is you plot the data. And so here, this is gonna be a slightly different plot than the previous one, because we don't only have information about like one thing, we have information about, so the one thing before was number of rooms. The 2 things we have information about now are the 2 different chemicals. So the first chemical is proline, the second one is flavonoid. We're going to use one axis to represent the concentration of each chemical. And then we would technically need like a third axis to represent if it's Barolo or not, maybe like 1 or 0. But instead of using a third axis, because that would be hard to plot, we're going to use colors. Okay. So here red means it's Barolo, and blue means it's not Barolo. Okay. So you can think of that as like a third axis, but we're using color to indicate that. And so you can already see here that maybe a line isn't the perfect way to classify this. Or sorry, like before we had this line, whatever. Okay, let's go into the next part. So here's one algorithm you might implement, which is just using a line to split these 2 classes apart. Okay, and this is called like, this would be called like a simple, doing some simple learning. And you produce this line, and maybe here it's not the best, and so something more complex maybe actually does better, which is like this like maybe more complicated kind of region here. Okay, and so finally, what this like the question is like, is this actually like which one's better? Which learning process was better for us? Well, what we need to do is we need to evaluate what is the quality of the prediction function that we output. And so what that would look like is we get some new data, and so these green and orange points are like new data, and you can see here that this line once again is maybe not the perfect thing, and it turns out that this square region is actually much better at separating this new data. So you can see here, like, we talked about this problem of overfitting before, but you might notice that, okay, maybe one way to like solve this problem is just have more data, because if I see enough examples of what things actually look like, so here I had 50 data points instead of 4, then I can use something much more complicated to properly like fit this region. And so that actually becomes more or less the moral of the story, which you're going to see throughout the course. And that is that, yeah, you can use complicated things if you have more data. And even in the previous house thing, if you just gathered more examples of houses, then you can use something more complicated. But you have this challenge, this kind of trade-off that happens between, can you really gather more data? And if you can't, then maybe you shouldn't use such a complicated thing to fit your data, because that might cause for you to actually predict new things poorly. So there's going to be this battle of how do you choose the right level of complexity for your like the thing you're going to output. Okay. So that's going to be like the main kind of goal of the course. So like, yeah, okay, let's you're going to see that in a second here, which is, so these two problems are going to be the main ones we cover in the course, which is they're both supervised learning problems, but there's regression and classification. And once again, regression, as I mentioned, that means the labels are continuous values. So that would mean like house prices. So that could be like any, let's say, number from 0 to who knows how many millions of dollars. And there's some notion of like ordering, like, you know, if your house is $1 million and another house is $1,001,001, that is pretty close. That's like a better prediction than if you predicted $1 instead. Okay, so in classification, there's no notion of ordering, and they're just discrete objects. So in this case, it was the type of wine. Was it Barolo or not? Is it a cat or is it a dog? Or like, is it a stop sign or is it a red light or is it a person? These kind of things. And there's no notion of order. Like if I predict like if I predict a person, that's maybe no closer to a stop sign than a red light is to stop. Okay, maybe that's closer, but like there shouldn't be any natural notion of order for these classification problems. Okay. So now let's return to his course outline, and hopefully it makes more sense to you, which is that at the start, we're going to talk about the math and this probability review. And for that, it's going to be to be able to actually formulate the problem, to like define what does the data actually look like. Like we're going to say, oh, the data is actually looks like a set of things, and we have to define what a set is and stuff. I guess these are all maybe simple things to everyone, but still good to review. Then we're going to need to define what like these functions are, and how do we actually like optimize over these functions, right? Because we want to find the best functions, so somehow we need to search over the space of functions. And you can see there's going to be some math tools you need to. And another thing is like the data, I said it was randomly sampled, but what does it mean for it to be like randomly sampled? Like what like you might have heard there's things called like a Gaussian or a normal distribution. There's other distributions like Bernoulli, like did it come from one of these distributions, or like what does that mean? So like there's all these little concepts that we're going to just like we're going to talk about in a math sense, but I'm going to really try to like in the examples in the math stuff, I'm going to try to like always point back to like imagine something like related to the problems we're actually going to study after. Okay, so that's how we're going to start. Then when we have these math tools, we can finally define what supervised learning is very formally, and that'll be great. That means we actually know what we're trying to solve in a very like rigorous way. And then once we know that, usually it's not that hard to solve it after you have a very precise definition of your problem. And so then we're just gonna like you're gonna see that the first ways to solving this is going to be like kind of very naive, and it sort of works okay. And that's what you're going to do before midterm 1, hopefully. That's the plan to get there. Okay, so you'll know the problem and you'll know some solutions to it. So then after midterm 1, you're going to be like, okay, how do we actually know if this was a good choice? Which means like when I see new data, does this thing actually do well, right? So that would be in like that plot. You would have up to midterm 1, you would have only produced like the actual like lines, the red lines, but you would have not actually like checked how they do on new data. So after midterm 1, you then are going to do this process of evaluating your functions, which means like getting new data and seeing how it looks and things like this. And then you're going to realize that, okay, now that I have this knowledge of how to evaluate what the quality of my function is, I can then change maybe the way I'm learning this function, because I want to like I know what's doing well, what's not, and I can kind of optimize for this thing that I actually care about, which is evaluating. Okay, and then you're going to introduce new ways of learning to achieve this, and this is all going to be with regression. Okay. Then you're going to have midterm exam 2. And then after that, you're going to repeat basically everything all over again with classification. And that'll be interesting. And then after that, if we have some time, we'll talk about these language models. And just like very briefly, these language models, all they're doing is like, you've seen this classification thing, but so what did the classification thing look like, right? It like got some context, and then it had to predict what is the next like wine or whatever in this case. Well, with the language models, it has like this prompt, which is the context. And then all it does is it predicts what's the next word. That's literally all that it's doing. And then all that you would do is you would, in here, instead of having like 2 classes, you can imagine there's like a lot of words you can predict. And then this learning program here for these language models like ChatGPT and stuff is no longer, well, it's actually exactly what these like complex ones were, which is neural networks. And so we're just like, we'll briefly brush over like maybe this relationship. And hopefully that'll be like exciting to see that everything really does tie into everything you learned. The only thing you need to do is just replace the thing you output, because you're going to learn about like simple prediction functions to output, which are like linear and so on. And you just replace that with neural network. So all that's left was going to be like, for future courses, is to learn what is this neural network thing. Okay, and then you have the exam. And okay, yeah, so that's really all I wanted to highlight. And the next few slides are just like maybe a little bit of a teaser and something fun for you to think about and stuff like that. So before I get there, is there any questions about the course outline, whether you're sad about the fact that we're covering things, not covering things, I don't know. Okay, no other questions online. Okay, so now we get to maybe the fun part. Okay, so I wanted to mention, actually, all the code I wrote on that, which I told you that you guys are going to learn, I actually didn't write any of it. So all the code was generated by this other language model and stuff, which is called Claude. I could have easily used ChatGPT as well for this. So I just told it, like, can you write me this thing? Can you make new data points? And then write another thing. And so at this point, that's kind of cool, right? Like, I didn't need to do any of this work. But you might be wondering, like, wait a second. Like, I told you that you're going to be writing the code for your programs here. And now I just told you that Claude wrote the code for your programs. So what's going on? So the thing to keep in mind is that, like, where did Claude come from? Well, where Claude came from is actually, there was another process of, there was some other experience, which was like the whole internet, and there was some other learning program, which then produced Claude, okay? And then Claude is this program that has knowledge. And what knowledge does it have? It has the knowledge to, like, write code or write text and whatever. And so then that was used to then produce another program, which was a learning program, to then produce the lines and stuff you saw. So this gets, like, very, very, I don't know, maybe sort of philosophical. You can, like, think about it, whatever. I think it's an interesting observation. And maybe one point to highlight here is that you should keep in mind there was some humans that had to write this code. So, like, there's always a starting point of, like, someone had to write the program that actually learned to produce this other program that can then do these other things and so on and so on. And so you can do this part. That's maybe one motivation to work on this stuff, but maybe that's not so satisfactory to everyone. And so then I thought I should probably explain why should you learn to write programs that can learn if there turns out to be other programs that can write programs that can learn. And yeah, I don't know if I have the best answer for this, but I think it's like a valid question that you should all ask. And here's my answers that I came up with, which maybe you don't love. But the first one is, I think it's the classic answer everyone had, like, that's commonly used for when people ask, like, why should I learn something that is going to just become automated? And the usual answer for that is, like, if it becomes automated and something goes wrong with the automation, then you have no idea how to fix it. So then you know how to fix it. And that means something like, if it produces something and it's not doing exactly what you want, you have no idea, like, what, like, you can tell it to try to fix it, but then if it can't fix it, you have no idea what's happening. And you have no idea, like, if it produces some sort of output versus another, you don't really know why it did this. You can ask it, but then you don't know if you should trust it and so on. So yeah, so if you don't know, like, how it works, then you can't fix issues and stuff like that. So, okay. And then the second answer is, like, so I've been working on this stuff, like, as a PhD student for a while, and honestly, I think it's like, it's quite fun, but also it really feels magical, because, like, now instead of, like, giving the instructions to a program to, like, add numbers, which you already knew how to do kind of yourself and you expected it to do the thing, you're just telling it, like, look at this data and figure out, like, the instructions yourself. And somehow it does this sometimes. And it's like, it's pretty amazing. It's like, I don't know, it's like watching an animal learn, you know? You give it some experience and then, like, magically it produces some behavior that you're like, wow, I didn't know this before. And you never, like, told it explicitly what to do. So that's my motivational part at the end of trying to tell you why this is a fun field. And yeah, that's the end of this class. So hopefully you guys come back to learn more.